Hello all. Welcome back to Python Challenge for All. Okay, so kind of today's new topic, lesson 98, recursion and Fibonacci numbers. Have you heard of these? Okay, let's start. So recursion, let me explain what recursion is first. It's kind of a different concept opposed to iteration. So iteration is kind of, they making loops using fors or whiles, right? So recursion is a way to, for example, define a function that calls itself within its own definitions. So let's think about a case example. For example, we often use as an example a factorial function, fact of n, to compute the product from 1 to n. So let's think about it. So for example, okay, let's make a box here uh, to name it as recursion and Fibonacci numbers. Good. So for example, if we define factorial function, we can define as this, the fact of n as, say, okay, return fact n minus 1 times n if n is larger than, say, 1, else 1. Okay, let's see how this works. Okay, let's define. So it means that if n is larger than 1, means if n is natural number n is larger than or equal to 2, it's returned as fact n minus 1 times n, otherwise 1. So let's see how it works. Okay, so for example, let's see fact 3. Okay, fact 2 is 2. Fact 3 is 6. So we can kind of make a list of all factorials, like for I in range, say, starting from 1 to, say, 10, meaning that if I write 11 here, so print, say, I don't like this, say I, and then fact I, and let's see what it makes. So it makes the factorial 1 is 1, 2 is 2, 3 is 6, 4 is 24, 5 is 120, 6, 720. So it's like the 120 is 5 times 24, and 24 is 4 times 6, and calculated like this. So this is how factorial works, okay? So let's see another example of recursion definition, Fibonacci numbers. So Fibonacci numbers are sequence where each item of the sum of the two previous ones. Very simple, right? So let's literally, yeah, we can hand calculate the sequence starting from 1 and 1. Next one is 1 and 1, 1 and 1 plus 1 equals 2. Next one is 1 plus 2 equals 3. Next one is 2 plus 3 equals 5. Next one is 3 plus 5 is 8. And continuing like this, we can define a Fibonacci sequence. So let's define a function to calculate the nth element of Fibonacci sequence as Fib1. Okay? It's simple, right? Let's do that. You can stop the video and try yourself. So it's like this. The Fib1 n is, yeah, quite simple. Return. Yeah, so usually write the non-terminating calculation first. So fib1 n minus 1 plus fib2, sorry, fib1 n minus 2. And this is for all numbers if n is larger than, say, 1. Else, sorry. If n is larger than 1. Else, they are 1. Okay? The first two are 1s, so this will answer that. Let's do the same thing as before. So it's like this. So copy it here, and instead of factorial, we can write fib1. Okay, let's run it and see how it works. So, a little different from, it should be greater than 2. Okay, I see. I should write 0. Yeah, we should start from 0. Okay, so the first two are 1, 1, and then 2, 3, 5, 8, 13, 21, 34, 55, 89. Quite simple. Seems it's slower than factorial. By the way, here's a trivia. What does the ratio of consecutive Fibonacci numbers converge to? It's an interesting one. You can try yourself and find out. Maybe we'll come back to this topic maybe next time. So this is kind of a homework. Well, first homework. You can work on it. So it's a kind of very famous story. You might know the answer. There's a keyword, golden ratio here. But I'll come back to this topic next time. So let's go on. The main topic of today is comparing computational cost, computational speed. So how we can kind of understand and predict the computational speed, computation time for large number of n. Okay, compare the number of operations required for Fibonacci calculations. And let's see how it changes depending on the algorithm. So here, we will try to measure, visualize, and predict the computation time for this fib1 function. You know how to do this. Okay, I will first give you some hint about doing that. To measure time, we need import time package. Okay. For visualization, as you know, we might use matplotlib as usual as PLT. But basically, let's see how the computation works. So we define a list of times to see how it goes. So let's see how, for I in range, say, 20, and let's run it. Okay. So let's print one by one. Answer is fib1 I. And let's see how it takes time by, for example, starting time is time.time. And then after each time, okay, we can do this each time for computation. So at each computation, we can measure time, and computation time equals time.time minus s time. So this way, we can calculate how much it takes to compute this number. It should be small, right? So let's print it and see how it looks like. So we print I, ans just in case, and C time. C time can be done by, say, F C time colon dot to F. Let's run this and how it works. Okay, this will print the times. Okay, let's run it. Oh, sorry. Float object is not. Time.time, S time, no, here. Okay, let's run it. Okay, it's quite fast. Up to 19, only 0.0 second. And your task is continue from here, say like 30, 40, and 50, and predict how much time it takes to compute up to fib1 of 100. Let's do it next time. So you try to do it, and let's see what your answers are. Okay, so please continue. Please come back next time. Let's continue. Bye-bye.